We are going to be learning TensorFlow together. I've been wanting for a while to make some tutorials, some video tutorials on TensorFlow, because what I found that even though there are tons of tutorials on YouTube, they are either too shallow or they did not really hit the points that I wanted to hit. And then recently I found that Stanford is offering this course, CS20SI, and this is the winter of 2017, and they made the slides available for anybody. So even though the videos are not online, but the slides are. So I thought I'll just use the slides, the great slides which have been made by Chip Huyen from Stanford, and we'll just follow along the tutorial. So the general idea out here is that I'm going to be just taking the slides from the Stanford class as they become available, and I have been working with TensorFlow for the past year or so, and I'll just put in my thoughts on them. And this would be a good way, hopefully, to follow the Stanford class if you're following the slides, or to just learn TensorFlow from scratch. So without much ado, the agenda will have the same agenda, which is the overview of TensorFlow and graphs and sessions, two of the most important, and when you're starting, probably the most mind-bending concepts that you will come across. So this is Chip. Thanks a lot, Chip, for the slides. Thanks for making them available to the public. And I'll go, if there are certain slides which are not directly applicable, I'll just go through them very quickly. Now, so if you're here, you probably know what TensorFlow is, but it is a library for numerical computation that has been open sourced by Google. So Google Brain Teams uses TensorFlow within their own team, and they have a separate branch for that they use, but they have open sourced quite a bit of it, and the delta between what they are using and what they have open sourced is just because of the complexity of making that code base open source. So that's what they have put out. And the basic idea out here is that we are going to be creating graphs and making numerical computations on top of these graphs. So TensorFlow has a huge suite of functions and classes, and it will enable you to build various models, be it deep learning models or shallow models, whatever you want, logistic regression, linear regression. You can build pretty much anything from scratch in TensorFlow. And the interest in TensorFlow has just exploded since it was released slightly over a year ago. Now, there are many deep learning libraries. TensorFlow is one of them. Torch is another from Facebook. And now recently, 2 days ago, Facebook open sourced this framework called PyTorch, which is, there is a Python API for Torch. And one of the things that they put out in the release is that PyTorch, or Torch in general, would allow you to build dynamic neural networks, whereas TensorFlow is more suitable for static models, where you know the model when you're starting, you build it out, and then you run computation on it. There are others like Theano, Caffe, the Microsoft version of everything, CNTK, etc., etc. But what we are going to be going for, obviously, is TensorFlow. One of the best things about TensorFlow that I feel is that it has this Python API, and I love Python. I love coding in Python. The other thing is that you can deploy the model anywhere. You can deploy it on CPUs, GPUs. I have a GPU box with 4 Titan X GPUs in there, and TensorFlow just works very well with that. It can use one or more GPUs in parallel. It also has it can also be deployed on Android, iOS, all kinds of platforms. Checkpoints, which is another, well, checkpoints is something that in one way or another is available with most deep learning models. The whole idea is that as you're running the model is going to be saving its state every now and then, so that if you're running a multi-week or multi-day model and your power goes out, it's not that you'll have to start everything from scratch. So checkpoints save the state of the models so that the models can start from that point down the line. Auto differentiation is pretty much every deep learning framework will have to have. Without that, it's not much fun. And I don't know if you guys have tried to write the back propagation layers for your networks from scratch. I have done that, and it's extremely illuminating. So I would really, really advise everybody who has not done that to go ahead and try to write the various backpropagation layers for the forward and the backward passes for various layers initially to get started, so that you have an insight of how easy things like frameworks like TensorFlow make your life. Obviously, TensorFlow is being used by a huge community, and it just keeps on growing. Lots of companies are using them. The list keeps on going up. And let's go through some of the projects. So this is neural style translation. It's an amazing paper where you take two images. Let's say there is this image of this lion, and then there is this other classic. And what the network does, it takes the style from the masterpiece. Let's say whatever I'm sorry, I don't know who the painter is out here. But it will take the style from this painter and the content from this other picture of the lion, and it would come up with this kind of a fused image. And the network just does it for you. So it's an amazing, amazing paper that came out earlier last year. Now there is a lot of work that's happening in generation, be it handwriting generation, which is what is being shown in this slide. And then recently I came across this paper called StackGAN, so Stack Generative Adversarial Networks, which takes in text such as I need a bird with red beak and yellow breast, and it will just generate that the image of the bird. So there has been a lot of work on GANs. So the StackGAN paper actually generates higher resolution images. Amazing, amazing paper. Wavelets, that has been in the news quite a bit recently. And hopefully the class gives everybody the ability to be able to just piece together projects such as what we just talked. So in this lecture, we will go through the graph, the computational graph model that that TensorFlow has. We will go through some of the built-in functions, and we will learn how to structure these models from a deep learning perspective. So going through some of these slides. So there are some books being mentioned out here, but what I have found is that the API is really fluid. So it keeps on changing very, very fast. So your best bet is to go to tensorflow.org, and whatever you want is out there. So just use that as a source for the latest APIs, etc. Okay, so once you set up TensorFlow, and I would assume that you can just follow the instructions which are laid out on the TensorFlow website. You just import TensorFlow STF in your Python shell, right? Now there are many different libraries and higher level abstractions that are coming out on top of TensorFlow, such as TFLearn, TFSlim, Keras, Pretty Tensor, etc. Now, They do make your life simple if you are trying to build models where everything is just in your control. Well, let me try to, for simple things, these high level abstractions really work well, and they are getting better and better in the sense that they can handle more and more complex things. But initially, I would suggest just learn the darn thing from scratch, because it will give you the best bang for the buck as far as learning what's happening under the hood, so that you can piece stuff together. And you do want to build models which you came up with. It's not just the off-the-shelf models that you want to implement, but you want to be able to build models from scratch, and learning TensorFlow from scratch is going to give you the ability to do that. So let's talk about graphs and sessions. So one of the major things about TensorFlow is that it separates how you define your computation from the actual execution of the computation. So what does that mean? Basically, when you're writing a model in TensorFlow, you will be assembling a computational graph. And once you have done that, you would use a session to execute whatever operations you laid out in the graph. Now, this will become very clear in the next few minutes, so just hang on. Let's start with the basics. Tensor is basically a n-dimensional matrix. If it's zero-dimensional, it's just a number, 1, 2, 2.5. That's a scalar. That's the zero-dimensional tensor. 1D tensor would be a vector, which is, if from a Python perspective, it's just a list of numbers, 1, 2, 3, 4. 2D tensor is a matrix, and the dimensionality keeps on increasing. So any n-dimensional matrix is a tensor. Now, once we let's start with this concept of how the whole computer generation of the computational graph works. So let's say we have, once you import TensorFlow as TF, you come up with the statement a is equal to tf.add, which is an operator, 2 comma 3, right? Now, if you were to visualize it using TensorBoard, by the way, TensorBoard, an amazing visualization platform that is already built into TensorFlow. So highly recommended. We'll get into, as the lecture progresses, we'll get into how to use TensorBoard, but it allows you to visualize your graph very easily. So highly recommended that you start using it right away. So when we do a is equal to tf.add 2, 3, and we try to run this, what will happen when you visualize using TensorFlow is that you'll see something like this. So there are these two nodes that come up in the visualization, x and y, and then there is an additional node which says add. So for now, let's just assume that these x and y are 3 and 5, and in the TensorFlow visualization, the nodes are the operators, variables, constants, etc., and the actual tensor values are on the edges. So this is the visualization that shows up. Now, when you actually run this tf.add 35, let's say a is equal to tf.add 35, and you try to print a, you see that it doesn't show up with 3 plus 5. You would expect, if the computation did go through, you would think that it would come up with something like 8, but it does not. At this point, we are just creating the graph that we are talking about out here, right? So a node has been created, add, and this is the shape which is being inferred from the addition, which is 3 plus 5. So it's scalar, so it's a zero-dimensional tensor which has the shape of just empty brackets, and it is the d type is in 32. So now if I were to do b is equal to tf dot add 3.0 5.0, and you say, what you'll see is now another node has been added which has incremented this. The same, it's still a scalar, but now the type is float. So the graph interpretation is inferring whatever data type that this tensor, this B tensor can hold, and in this case it's float 32. So the nodes in the graph again are going to be what are called operators, variables, constants, and the edges are tensors. And we'll go into the definitions of all of these different types of nodes that we just talked about. So again, out here, this is what I just showed you on the Python console, where when we are adding 3 and 5, adding a, you'll see that a node has been added, add a scalar and a int 32, which is the default integer type in TensorFlow. Now, if we really wanted to get the value of a, if you really wanted to get that 8 out here, what we would do is to create what is called a session. So you will instantiate a session and you would run the computation within that session. And the whole idea of sessions is that once you create a session and it takes all the resources, even if there are multiple GPUs, whatever, it takes care of getting all the resources in place to run a particular computation. And now when you run that actual node of the graph within that session, it will compute the graph and will send you the value back. So what you would do out here is you would just instantiate a session using this tf.session command. And now when you say print session.run a, so session.run, and then whatever you put in the parenthesis is going to be either the whole graph or a certain node within the graph. So here we gave a node which is a, and what this will do is actually run that computation, and the print is going to be printing out the value of 8, and then you can close the session. So if you say ses is equal to tf dot session ses dot run a, and it will come up with a value of 8, right? And let's close the session for now to release all the resources. Now, what happens at this point is when we put in the command ses.run a, what TensorFlow is doing is looking at that value of the node, which is a, and now it looks back, since it has this whole graph available to it, it will look at whatever is necessary to make this computation going. And it will go ahead and compute that, and then it will finally compute the value of a. So you can imagine that if there are many more nodes, it will go all the way back and start computing from whatever is required, and then finally give the value of 8. So more on that. And so one of the things that is being shown in the slides out here is, instead of doing the explicit session.close, we can just use the with statement in Python, so that in out here with tf.session as ses and session.run a, once you come out of the with clause, the session is automatically going to get closed. So similar to what you do for files, etc. in Python. So tf.session is it gives a session object, and this basically encapsulates the entire resource environment for all the operators to execute in. The tensor objects, the various operators, everything is executed within the environment of a session. So if you were to take another example where we have x and y, 2 and 3, Now we define an operation tf.add xy, operation 2 tf.mul xy, operator 3 is tf.power of operator 2 op1. So basically, if this is xy, this is x raised to y. Now with tf.session at ses, we are calling operator 3 session.run operator 3. So what happens from the TensorFlow perspective is this graph was created when we went through these five statements, right? So even before the with tf.session, this graph got created. Now, as soon as we try to run op3, which in this case is the power, now TensorFlow knows that it needs mul, and for mul, it will need x and y, and it's going to calculate op2 in this case, right? It also needs that op1, which is the tf.add_xy, so it's going to calculate the value of x plus y using this node add, and now when it has these two nodes, it's going to calculate tf.power op2 comma op1. So out here you see an example where when we start, all these calculations happen when the session.run op3 is called. So it's not like all these values are pre-calculated by TensorFlow and cached somewhere. That's not the way TensorFlow works. What it will do is it will wait very lazily for the need for these calculations to show up, and then it will run through the graph and make this calculation. And another interesting thing happens is that the graph can be very complex and it can have multiple nodes, but the power of this lazy evaluation comes from the fact that not everything needs to be calculated. So if you go through another example out here, where the op1 is again add, op2 is mul of xy, and there is this other node, we are calling it useless out here, which is op1 multiplied by x, right? So 2 multiplied by x plus y, and which is out here. And op3 is the same that we discussed in the slide above, which is tf.power op2 op1, right? Now, out here, if you're trying to calculate op3 by using session.run op3, what will happen is when you go to op3, it will see that all I need is op2 and op1. And for op1, I need to do this calculation of add, for op2 mul using x and y, and so it will go ahead and calculate op1, op2, and right then everything that is necessary to create the recipe of op3 is in place. So at that point, it's not going to go ahead and even calculate this node, which is the tf.mulx.op1, which is the node called useless. It's not needed, and that's where the power of this graph data flow computation starts revealing itself, because we only calculate what is needed, and that saves a bunch of computation as we follow along deeper into the models. So if we go ahead and provide a whole list of operators, so what session.run takes as if you were to look at the definition of tf.session.run in the actual TensorFlow code, and sometimes it's very illustrative to do that whenever you're not comfortable with certain API or whatever, just go for the source code. It's all available on GitHub, and it will give you it's extremely well documented, very well commented, etc. So once you go there, you can get a deeper insight into what that particular API is trying to do. So when you look at the tf.session.run code, you'll see that the first argument is this that it's expecting is this list called fetches, right? And whatever nodes, so once you create this graph, let's say useless, op3, op1, op2, whatever you need, what you all you do is to provide that list of nodes within that within the fetches list and pass it on to run. And then TensorFlow is going to calculate all these different nodes that you passed in, and it will give you the results back as a list. So for example, if you did want to calculate useless, you could have passed in OP3, you could have passed in useless, both these nodes as a list, and passed it to session.run, and you would get OP3 and we are just calling this variable not useless, and you would have gotten this result back from TensorFlow. The other beauty about modeling our computations in this way is that since it's a graph, you can literally point various nodes to various CPUs or GPUs, and that computation would run in parallel across multiple CPUs, GPUs, or devices. So this is another thing that we get out of modeling our computation as a graph, where any of the subgraphs can be just forked off to a separate computation device. This can make a lot of these things extremely parallelizable. And this is an example of how we can put a specific graph on a specific GPU, and I believe we will go into a lot more detail down the line on this. But you can just create this device, tf.device GPU. So if you have a machine with multiple GPUs, they go as GPU 0, 1, 2, 3, etc. And you can just put in a certain graph on a certain GPU, where with this command tf.device GPU2, and now whatever you are instantiating, the node elements, which is the tf.constants out here, and the operators, which is tf.matmul, which is also a node, by the way. And you can, these devices, this computation would be running on GPU2. And now when you create a session, this is the recipe for creating a session where the resources are being sourced from that one particular GPU for in this case. And yeah, the rest of the computation progresses exactly the same way, which is session.run-c, which is going to calculate tf.matmul. But looks like we are going to go into a lot more detail on this down the line. Now, what if we want more graphs, right? So the session, so whenever we start writing our putting in various operators, starting to create our graph, TensorFlow provides this default graph that we are actually putting our nodes and our variables, etc. in, right? And when we do the session.run and then put in an operator like op3, what we did earlier on, the session is actually using that default graph. So if you want to have multiple graphs, and Chip seems to be having a very strong bias towards not having multiple graphs, one of the use cases where I see where we might want to have multiple graphs is, let's say, ensembling is a very common use case in deep learning or machine learning in general, right? So you might have a model which for a particular one particular task, you might have trained completely different models. One is a CNN, one is a RNN, pixel-based RNN, or various models can be put in place to train for a specific task. And now during inference time, what you want is you want to be running all these different models in parallel, let's say. And let's say if you have 5 such models running and you want to have a majority vote to find the actual classification, that is something that I would think can fall into the use case of having different graphs, because all these different models are completely separate, and they will require their own sessions, which goes ahead and gets all the resources required for running that particular graph. And one of the things about these sessions is that They are very greedy in the sense that for my machine, when I just run this by default session.run, and let's say I'm trying to train a training job, it's going to go ahead and get all the resources. It's going to try and hog all my GPUs in one shot. So there are ways of actually making sure that your program is just looking at one or two GPUs, but that's one of the things that you have to take care that if you're explicitly running multiple sessions, all these sessions are going to go ahead and try to get as many resources as possible. And one of the other things is that all these different sessions are completely separated execution environments. And if you want to have data passing through them, you will have to come back to the Python NumPy layer. And it becomes pretty hooky when you're trying to make it work in a distributed setting. So looks like Chip really wants us to use one session, so we'll go with that. And the way you create a graph, if let's say we want to have something other than the default graph, is using this API, which is tf.graph. And now when we want to add operators to a graph, you would make it you would set it as default, and the way to do it is g.asDefault. This is the API you'll be using. Now, if you're not using any of these things, if you're not instantiating this, by default, there is a default graph. So this is not required. And when you do the x is equal to tf.add35, it's going to add this node to the default graph. But now, as we want this to explicitly happen within the context of a certain graph, we will first instantiate that graph. We will make that graph as default. Now we can add in whatever we want out there. Now, for the session, when you instantiate the session, you would pass tf.session graph is equal to g. So you will actually pass this keyword argument of lowercase g to this, which is something we have out here. And now session is going to be looking at this particular graph g, and now when we run the particular node x, it's going to be executing that graph. So again, another example out here, we instantiate a new graph, set it as default, add some operators out there, a is equal to 3, 5, tf.add_ab. Now, when you give session is equal to tf.session graph g, so now this is our session is going to look at this graph, create the entire execution environment around it, and you can run whatever you want out there, and then you close it. And if we just want to get the handle on the default graph, we just use this API to get tf.get_default_graph, and that you can save in this variable called g. So this is the default graph that if at any point you want to get a handle on the graph that you have been creating without instantiation or anything, you can get a handle of that. Or if you had created this graph and then set it as default, then this API will give you a handle back on that graph if it's needed. So another important thing out here is not to mix the two graphs. So let's see what we are trying to do out here. We instantiated let's call it a user graph out here, g is equal to tf.graph. But we did not set it as default. And now we are adding these ops, a is equal to tf.constant 3. And so this got added to the default graph that TensorFlow provides, right? Now we set this new graph that we created, g as default, and we add b in the context of this graph. And this is a bit hooky because it can get confusing very, very easily. If you want to do something like that, just get a handle on the default graph out here, which is g1 is equal to tf.get default graph. We basically get that handle initially from the default graph that TensorFlow provides. And now we create another graph, and now we explicitly with a with statement G1 we set it as default. We add ops out there, and now for G2 we add we set G2 as default and then ops out there, and this is better, but probably if you're doing simple things like this, it's always possible to go through with one graph instead of having multiple graphs. So one of the biggest advantages of graphs is that we can run the computation of subgraphs, and subgraphs can go all the way down to one particular op of let's say there is a op that we have put in x is equal to tf dot constant 5.0, right? And that can be a 20 layer network, but I want to just execute that for whatever reason, then I can just do session.run x, and it will just run that one part of the graph, right? Rather than running the whole thing. So this is one of the biggest things. And other reasons are more internal, which is all these different graphs, once it helps writing the library for auto differentiation. And also we went through that case where these different computations, these different subgraphs can be forked off on different devices, different GPUs, and TensorFlow also has a distributed mode where it can run across different machines. So once you have the computation described as such, a lot of these things are a lot of these things we just get for free. So we'll get on to the next class, and the major things we want to remember out, the takeaways from this session were, well, no pun intended, sessions and graphs. So the way we do things in TensorFlow is we set up a graph of computation, and then we instantiate a session and we run the a subgraph of that graph that we created. And by definition, when I'm saying subgraph, the full graph is can also be run like that. But this is the major takeaway, and then we'll go into more fun next week. Thanks a lot.